Okay, welcome everyone. Welcome to this luncheon panel, which is discussing the theme of EDA, electronic design automation, the past, the present, and the future. I'm George Gielen. I'm from KU Leuven, University in Leuven, and I'm the VP, Vice President Strategy of the IEEE Council on Electronic Design Automation. And this council is the main body within IEEE that deals with design automation, security, trust, validation, test, and all that. It has 7 journals that we sponsor and many educational resources that you can find freely available on the website. We have also 19 local chapters with local activities in different places around the world. And we sponsor major conferences like DATE, DAC, and so on. And we recognize individuals with several awards. And we participate to standards in the EDA field. And if you want more information about that, you find it on this website or this QR link here. We do this panel at the occasion of our 20th anniversary. The Council on EDA got created 20 years ago. And so we are happy to celebrate that with all of you at this panel. Now, EDA is dealing with support for creating chips and electronic systems. And if you look at the market sizes, we see that the EDA market size is about 15.7 billion in 2024, which kind of supports the semiconductor industry, which is $627 billion. And that supports the electronic products industry, products that we are all carrying and using on a daily basis. And that's $1.38 billion. So you see that this EDA industry has a leverage factor of 40x to the semicon business and 88x to the electronic products business, as shown there in that picture with the little mouse, the EDA mouse carrying the entire industry. So what we will discuss in this panel is what are the major achievements, some major achievements of this EDA industry in the past years, and what are challenges ahead of us in the coming years, as we will see that. And the panel members explaining this are from left to right on the screen. David Atienza, who is a professor at EPFL in Lausanne, Switzerland. He will be followed by Luca Benini, who is professor at ETH Zurich in Switzerland. Then we have Valeria Bertacco. She is at the University of Michigan in the United States. And finally, we have Rolf Ernst from the Technische Universität Braunschweig in Germany. And they will give, in a few minutes, their main points about achievements in the past and challenges for the future. And we start with David.
Thank you very much, George, for the introduction, and thank you, everybody, for being here. Like I said, like what was said, so the idea is to try to sum up some of the main areas where we have been actually great achievers, I would say, with the little mouse to support the current chip designs that we have. And for me, of course, it touches upon my heart. We were thinking about 20 years back when EDA, the Council on EDA was created, I was thinking about, and came out 3 areas. One is conquering the energy challenge. We did that once. Then it created also the rise of thermal problems, which we are even seeing more these days. And finally, we had the problems of durability. So if we think about that, well, in the early 2000s, we have very clear spread of creation of these multi-core chips that now are everywhere. So we have these MP-SOCs. And then when we started looking at them, you have a lot of issues regarding the design of the complex hardware. As you see that you have here, one of the most popular ones at the moment, the Niagara broadband processor, with uniform cores, but still creating quite a lot of issues on the thermal and power perspective. And then you started seeing that what we were doing at the moment for chip design were not really good enough, because we had suddenly heat that was actually a side effect of power generation or power consumption of these chips that were actually creating that single chip you could control what it was doing more or less, but when you put all these guys together on top of that, you put the software that was running in a very, you let people design whatever they want. In the end, you get extremely irregular hotspots. And actually, there was a very big challenge that already made us do one big transformation, which is, okay, so it's not anymore about layouts and chips, but you also have to think into account physical constraints and hardware and software designs. And then that was already one major request from the chip manufacturing industry that came to us as a community. And then you could see that the interaction between hardware and software was not at all present. So what was happening at that moment is that, well, the simplest way we just put cooling. And you see cooling, huge fans. Otherwise, you will get a situation with the thermal runaway and situations like this. Very popular at that moment picture where you see one chip burning out. You can have other ones where you see people frying eggs on top of the computers. There was also another one, very popular one at that time. And then we had to do something. So as EDA community, we started thinking about system level. And that was one of the main areas where you start thinking about applications, you need to think about the architecture, and then later on we were able to really link it to physical design. At the moment it was really something unheard of. People were not really doing that. They would say you will compartmentalize and everybody designs one piece, which is the simplest way to make the whole design process ready to be done by groups, so you can actually do it, but it was obviously not working. So we had to do that. We have to create what was concept the early design phase exploration, where you include in power and thermal analysis and the tools. We created the tools that will actually be able to propagate these requirements coming from software. You will have the power stimuli from software that was actually then included in the design of the hardware. And that created, in the design phase, a very, very nice loop for the first time between hardware and software interaction. And I believe this was having done for the last roughly 15 years. And we see that this has created very interesting analysis you could do in early phases of the design, understand how the software was affecting the hardware. You will understand how this will actually create different hotspots at the runtime, and you will be able to predict that at design time. And actually our community, with not too many designers with respect to the actual manufacturing teams in TSMC and some others, were able to create situations where we understand whether it was thermally unstable, the design, and we will make formal processes to actually guarantee the resilience of the chip against power and thermal constraints. And then you could have situations where you have exactly the same chip, you're simply doing another way of doing the design, plus also indicating the constraints to the software designing, to the software designers. You could actually suddenly, you have thermally controlled MPSOCs. So this was something, a very major achievement. We control power and thermal, and going back to this because now we have in this AI era, and you have started hearing people say, oh, we have the problem of power and cooling. I said, hold on, we have been doing this for 20 years. So I think you need to have to give us enough resources for doing that again. And I think it's one of the areas where we actually are. You can get these thermally controlled MPSOCs. Why cannot we do that the same way for the new systems that we have? So now we can have these type of solutions that were done, I would argue, 15 years back. We started doing that. That is now the bread and butter of any data center. You have water-cooled data centers and racks, pretty much used everywhere. And then we did it, no matter what they want to claim. What NVIDIA is designing now, the new GPUs and the things that they have with liquid-cooled solutions, is coming from us. So, and I say really us, the community that is a date and what we have been doing with the Council on EDA. Now, if we think about the next frontiers and the challenges, and I'm really very excited about it because I think there was a moment where I said, well, EDA tools are becoming so stable and mature that nobody wants to EDA. And I always tell my students is this, that you have plenty of options. Because if you think about the new 3DI chips that everybody talks about, you think about this heterogeneous design that try to copy the brain, which is roughly, and I would argue, putting a small bold numbers of 14.32, we are 160 times better than what you have today in any of the NVIDIA state-of-the-art GPUs. So you see, as a comparison, you have the human brain, which is around 20 watts. It does more than 10,000 teraflops. If you take NVIDIA H200, it's around 700 watts, which is 67 teraflops at 32, at FP32. You take FP64, is around 17, so it actually works. basically to replicate the brain, with the current design tools, if they don't need us, it means that you need this twice. So I think they need us. Now, we're going back to the keynote this morning, and we had actually seen that, okay, the first thing is that we cannot go flat. We need to go three-dimensional. And second, we need to solve the problem of cooling. So if you think about that, we need to first find ways to actually take what we are designing in this community. And I show here one example of Professor Subhasis Mitra with the new next 3D thermal solution they are proposing. What you see, it was presented at DAC last year. And actually it's interesting because I have seen a few people, but not too many still in the chip manufacturing and particularly electronics design taking up this thing. But if you think about monolithic 3D, it's a fantastic solution, but you need to give us funding for that. And actually the final thing is that you create that, this is the manufacturing, but then you have to solve the problem of heating, because heating is multiplied by a factor of 10 to 12 in these solutions. So again, I think we can do that. Can we solve the problem? I think yes, but we need to think, and that will be my last, and maybe only political statement, we need to do it all together. So these boundaries that are creating between Europe, US, China, I don't understand it. Simply because when we solved the problem of power and thermal, and I recall correctly the teams that were working on that, there were 2 universities in Europe, 2 universities in the US that we were one of the groups, and we have like 5 students from China and Asia. And if we didn't do all these things together, we would have managed. So if you now start creating silos and we need to work in isolated ways, it's not going to happen. So you really want to have AI, we need to have, and that is a generated image from generative AI trying to show how the world was 300 million years ago. We were one single block. The tectonic plaques were all one until we started splitting. I don't think it's a good idea to keep splitting it on our side. With that, I conclude. Thank you very much for your attention.
Good afternoon, everybody. It's always a pleasure to be here back, feels like home. So, I think quite naturally, when I've been asked to think about these topics that have been impactful 20 years ago and they still are, clearly for me the idea was looking into interconnects. And the NOC concept paper and papers were conceived just a bit more than 20 years ago. And in my view, it was one of the most transformative technologies that have been adopted by industry. Virtually now, every system on chip of complexity above a few million gates is designed using some form of a network on chip. And network on chip design automation, even though as a single market has not been a huge market, is pervasive everywhere. Everybody wants to design an SoC, must have a solution to automate and streamline the design of the interconnect. What, in a sense, makes it still a very, very current problem is the heterogeneity of the needs of the interconnects. As systems become more and more heterogeneous, forced by the energy crisis, so this specialization trend in creating acceleration engines that can be distributed tied to the processors like tensor units, as extensions to processors, as coarse grain accelerators, all this heterogeneity creates a huge interconnect design and synthesis and design space exploration problem. And so I think it was conceptually clear 20 years ago, but it's now extremely concrete, extremely challenging problem, and the challenge is not going to go away. So today, fundamentally, the big transformation is that all the major companies designing large chips for the cloud, for AI acceleration, and so on, have realized that the limit of the chip is too tight, and everybody is moving from chip to chiplets. And this also implies looking at the architecture in a different way, where there is a continuity in terms of accessing memory, accessing the memory hierarchy, storage, but also remote computation capabilities, starting from a core, then into a relatively tightly coupled set of cores and accelerator, a unit, a cluster, a tile, and then, assembling multiple tiles on a die, and then, making this die with the proper interfaces, a chiplet, and then assembling a system as a set of chiplets, heterogeneous chiplets, memories, compute, and different specializations and different cuts. So now this is what chip design has become today. Everybody that wants to design a competitive chip for the cloud and for the AI has to think in this way. And so this actually brings the analogy with the brain for the future. And if you look into in a sense the main difference between what we have today as electronic systems, these tightly assembled heterogeneous blocks of dies into a package, what is the main difference structurally speaking compared to the brain? The brain is a truly three-dimensional structure. It's not 2.5D dies that are stitched together close to each other. They are really on top of each other. And so, in my view, the future is coming. And, if you talk about people doing technology in the most advanced stages, like HIMEC here in Europe, they talk about CMOS 2.0. CEDA is talking about, monolithic integration. And, we research in Europe and we talk about it. In Asia, probably they do it. And, and TSMC is pushing very aggressively three-dimensional integration programs, and the next generation when you get to sub-2 nanometer technology, it will be, 3D multi-layer, multifunction. And in my view, the future of interconnects, the future of networks on chip is in this monolithic 3D. Heterogeneity, not a monolithic homogeneous layers, set of layers, heterogeneous, memories, devices of various types, and how we can structure this truly three-dimensional interconnects is the next generation EDA challenge, where I think we can be as successful as we were as a research and industry community in making a network on chip an industrial reality. So 3D network on chip is the next frontier. Thank you.
So good afternoon, everyone. So where we were and where we are. For the past 20 years, I think one of the key focuses of the industry has been about pushing the boundary of productivity. How many gates per month can a designer produce? Working gates. And so I did a little comparison between 20 years ago and now. I actually have a very specific memory of a design automation conference event where Art de Geus was giving the keynote address. And I couldn't pinpoint the year. I tried to look yesterday, but I was young. So it's about 20 years ago. And he was talking about SoC, how SoC will change the planet. SoC will unlock every bound, every limitation that we have in productivity today. So it makes a lot of sense with what Luca was also saying, right? To do SoC, you need protocols and standard and people producing IP and network on chips. So this comparison shows you a little bit where we were 20 years ago, where we are today. 20 years ago, we had behavioral compiler that was trying to do something, but actually, I think they closed, Synopsys closed or stopped selling behavioral compiler in 2004, so it's about 20 years. There were the first few companies that tried to do synthesis from C. Today, every major EDA company has a high-level synthesis tool, which is precisely an attempt to boost productivity by reducing the burden on the designers. There's been, I would say, at least 100 times growth in the power of formal and semi-formal verification. And that, what I mean with that is the scale of the design the formal and semi-formal verification tool can tackle, and the depth and number of properties that can be proven. So there's been, I would say, an enormous growth on that front. Of course, nobody's ever happy of what verification does, because to make people happy, we need to just say, it's completely correct, don't worry. We're not there yet. But if instead of looking with that lens, we look at the ability of these tools to do effective checking and verification, I think it has been huge. 20 years ago, we were starting to talk about symbolic simulation. I was working on BDDs. Today, we have this multi-engine tool that can check coverage, they can write assertions, they can really relieve the designer and the verification engineers from doing a lot of the work. I'm sure you all know that in any design company today, there is one designer and then 7 or 8 people who do verification. So if you help the verification people be more productive, more effective, you solve the majority of the problem. The designer can keep working the way he's working today. It's just 1 out of 8. And then SoC was not a thing 20 years ago, and now there is a very rich market and a very rich industry offering IP components, verified IP component where you get the IP and all the verification tools on them, standard interfaces, network on chip or complex situation. Even if we've done all this progress in design productivity, I think that's still the #1 pressure on the industry. We still need to be able to be much more productive. The cost of the design is largely driven by the number of engineers you have to put on the job, so being able to be more productive in producing bigger chips with fewer people is still the key aspect. And today, we started to have LLMs that can write Verilog code for you. So wouldn't that be a great solution? So this is an example. I hope you can read. This is an example of guidelines you can give to an LLM. My students actually recently did some tests, and they tried to design some small circuits with LLM. They tried 3 different engines, ChatGPT, DeepSeek, and Google Gemma. You first tell him, act as a professional Verilog designer, because that's never a given when you're working with an LLM. So it has to be clarified. An LLM doesn't know if you're joking or what. So this is a very simple description that should produce a square wave signal. So you specify the inputs, the output, and then there is a little paragraph here under implementation that tries to describe in English what to do. We've done 10 different designs. I'm showing here just the results with ChatGPT, but we run the same description to 3 different engines. So we get a Verilog design out of it. Then we try to compile it with design compilers. Most of them can be compiled. And then we try to run a test bench. And this is, I cannot claim that is a complete correctness, but basic test benches. Some of them, about half of them can be verified to be correct, and some others do not. Indeed, the general sense that we get is that when you start combining combinational logic and finite state machines, the LLM gets beyond their ability. So where are we at? We are at the point where AI can help us design some fairly simple designs, and the quality of the design is really low, much lower than a human being. So what can we do with that? I would say, just seeing the trends of LLMs today, I think the ability to tackle more complexity will come very soon, 1 to 2 years. I think the quality will remain wobbly. It's just not in the nature of LLMs today to care too much about, I'm saying quality, but really truth. They invent citation. It's just because it's hard to distinguish true from false when you are just reading a corpus of data to learn from, and you never really know what can be trusted. In addition, it's part of LLM natures to have to work on these English descriptions, which are not very accurate by themselves. That's why we have Verilog, right? If we could completely specify design by writing a paragraph, life would be very easy. So I think it's going to be very difficult to boost the quality of those AI-generated design, which brings to my point that maybe the biggest focus we should have in the next decade, I hope it's not going to take 20 years, is really to accelerate the productivity of verification, provide more tools to do verification. Also because if I'm a designer and I say, okay, I'm going to use AI to do design, then AI gets to do the design, and I'm stuck verifying the stuff that is so buggy that it's going to be a burnout for me. I don't want that job. I would rather do the creative job, and then AI verifies for me. So I think it's very important that we start doing more scaling and more automation verification. How? Abstraction, having formal verification for the simpler blocks, having design traveling with their verification, set of test benches, anything that can help in that spot. Another trend we're noticing, and I can only I speak about my university, we're already starting to notice these trends. Students who are studying computer architecture, who are starting to do some very simple hardware designs, in the last 2 or 3 years, we notice a decline in their learning. They often come to office hours and they ask the instructor to explain what their design is doing. Which means they go and they get an LLM to provide some design, and then they spend all their time understanding somebody else's code, which again, is a lot harder than writing your code. I also claim that it's a lot harder to learn because I learn much more by writing than by reading, right? So reading other people's code, maybe I'll get to the point I understand, but I don't know how much I can retain that information. And then these poor students, again, they're stuck just doing the verification of something that is extremely buggy. So I have to be honest, I have not figured out how we're going to solve this problem, but there is a clear need to overall how we educate engineers so that they can be productive designers in the context of these tools that have some values, but they're also not very stable. And maybe think about what would be the role of the designer in 20 years. And I hope it's not going to be just to debug what an LLM is doing. But definitely the way we're teaching today is no longer working with the infrastructure that is publicly available for students. And with that, Rolf.
Yes, thank you very much, and also thanks for being here and inviting me. This is about the E-track. This is how I would like to start. So in the 90s, there was software that was basically application software, and that was hosted by operating systems, and this was all the software you needed, right? So there was a Windows system, there was Linux or Unix at that time, and application software was just very similar to what you had also in standard computing. But then this whole thing changed with embedded software. So there were real-time operating systems first. And today, if you look at the scene of software, you see that there is no larger chip around. All the things you have been hearing about this today only works with embedded software and related software tools to configure the system, to provide drivers, to interact, and when it comes to networks on chip, to also provide interaction with specific software for networks on chip, and more recently, beyond the chip in distributed systems, forming software there. So today, we can say that has been a pivotal role in handling the chip complexity and systems operation to a level where you can say without software that would not be possible. Now, Date actually was very active in this field, one of the first. So we had an important role as a scientific embedded software pioneer. So in 1999 already, when the internet bubble started, and everybody was only talking about internet, we had here at Date keynote sessions on embedded systems design with the CTOs from then Nokia in the middle of this trend, and also BMW that moved towards that trend already in the late 90s, and we decided to extend the scope of Date topics at that time. Now, we started in 2005 the embedded software initiative as part of Date, and you see here, this is also 20 years ago, when this, Joseph Sifakis, our Turing Award winner, and I started this initiative following previous actions from, for example, Ahmed Jaraya and others who had already started topics around embedded systems. So in 2007, the E of Date that was originally exclusively used for the term of Europe was assigned to the embedded software track, so we had all the 4 tracks defined. And then in 2018, it turned out that it was not sufficient to only look at the embedded software, but it was extended to embedded systems for the very simple reason to also include all the networking that was originally only network on chip and then later extended to other networking topics beyond that, including Ethernet and whatever you needed in this context. Now, this is a success story, and I can just tell we were among the first. The Embedded Systems Week only started later after 2005. It was in 2006, and then other conferences joined that trend. But DATE was definitely, out of the EDA conferences, the first one to really emphasize that. Now, I would like to follow up on that, what Valeria just said. I mean, this idea of productivity. And the question really, if you look around also in the reality of software design, if you write software yourself, you are not up to date anymore. Most of the software is configured from modules. You have support in AI for writing and configuring software. And there is a tendency towards extreme high productivity in software engineering. So what is our field then here? Now, I think, and I teamed up with other people, that autonomous system, the system autonomy is the next big challenge that goes beyond software. And there is a physical systems autonomy. This is a long-term trend that we have been observing for a while now. And this has to do with increasingly complex functions. The first one probably were the space people who started because of the lack of controllability. And then now we have robotics, we have vehicles, we have UAVs, and all these tendencies come together and they ask for more supervision, more control, and this is more and more answered by autonomy and autonomous system functions. There's another reason for that. The one is the distributed platforms are open, so there are many applications on the same platform, and there is no one designer that has an overview on everything. There's a convergence issue. Different types of functions like automotive, infotainment, whatever, is merging on the same network, for example. And there's the whole issue of integration that grows with the number of different functions and the size of the platform. The newer trend that comes hand in hand with the complexity is unknown things. So we have incomplete models of the system. To talk about industrial design in industrial environments, industrial automation, there has been coined the term of digital twin, which basically means you model the whole thing as a software model, but you find out later that this is incomplete because you don't know everything about your process. And then there's an uncertain and permanently changing environment. I mean, if let's say an automated car goes into a city, it meets other automated cars that have not been there before, and so on. So you ask for self-adaptation and evolution, but there's a problem with that, because at the same time you require these systems more and more to take over important and critical functions, and that means you require dependability all the way up to safety. So this is a contradiction that somehow this conflict somehow has to be addressed by formal methods. Now, you might say there are many people who say AI is going to solve all the problems, right? In particular, end-to-end AI. But there's also a slightly different aspect that I'm going to address now, which is basically the fact that system autonomy the challenges didn't go away. You still have the list of things that I showed on the top here, but now you also add things that learn and that really can be used to control and configure the platforms and manage the platforms with AI. This has been proposed even all the way to the tools that are doing that with using AI for tooling. But the problem is that it also adds to uncertainty. And we had a very nice keynote last year from Edward Lee from Berkeley University that was titled "Certainty or Intelligence, Pick One." If we control the intelligence too much, we don't gain much. If we control everything that we say, the system has to follow like in the classical automation that is shown in the bubble up there, then we don't gain much. If we look at the cyber-physical systems, we have all this environment that is controlling, and there is this idea of physical AI that has been coined by NVIDIA in particular, where you simulate the environment and then control it. This is something that you can do, but you still don't solve the autonomy problem. And there are various learnings and inference strategies for CPS. I just mentioned physical AI, which is basically still separating learning from inference phase, but there's also this embodied AI, where the learning should go to the field and be accelerated there, which of course challenges even more the dependability and safety side. And we had 2 years ago another keynote that was a main keynote in 2023, which was also related to the ASD track. That was the cyber-physical metaverse, and he was talking about controlling a complete car traffic by centralized knowledge and a centralized body of control units, AI-driven, and showed how the future could possibly look like. So this is the trend that we see, and I think the whole thing is moving above software now. Now, what has this whole thing to do with design automation? So why would we talk about the design automation here? First of all, we cannot rely on design time learning anymore. So we need at runtime support, in particular because we don't know exactly how the system will react to certain situations, so we have to control that. We know this from safety critical systems design, but it's much more challenging if you have to handle uncertainty, both from the environment and from the system itself. So we need modeling, monitoring, verification. We need protection against unwanted behavior and destructive emergence, which can happen if two systems that have never met before suddenly start to interact. We proposed in the past already, and I've seen that things have somehow emerged in practice, is a supervisory layer, a control layer that sees what the system is doing and then tries to interact. I'll be done in a second. So we need EDA tools and methods to control this uncertainty and to enable the controlled evolution and adaptation in the field. So we have to move, and this is what the drawing down right there shows, from the traditional design process to an enhancement where some of the tools and functions move to the field, where field means edge computing, cloud computing, or to the terminal device, doesn't really matter. And this is why we started in this ASD initiative at DATE in 2019, and we have a 2-day program here, and including a workshop tomorrow afternoon, which looks into the supervision problem of autonomous system design. So, thank you.
Okay. Thank you very much. This gives the opinions of the 4 members of the panel. And we have about 5 minutes time for questions from the audience to challenge some of these ideas, to complement some of these ideas. We have microphones if you want.
I have a question, but I want to...
There's a microphone over there. Subhashish.
This is a celebration panel and, wonderful points. Now, we should be introspective. Are there examples of things that you are shocked about or you are highly disappointed about what happened in the last 20 years? I have one, but I don't have to, talk about...
Anybody from the panel members who wants to answer this?
Yeah, I can say that this is the naivety in which people have run highly complex automated functions to vehicles and whatever systems we see out there. So I should say artificial intelligence requires a lot of intelligence and caution from our side.
Marilyn, you have a...
Do you want to speak near me?
So I apologize, I missed the first couple minutes, but I just want to make sure that since this is a 20th anniversary celebration, we remember that Al Dunlop was the guy who masterminded the approval process for CEDA and was the first president.
Okay.
Yes.
Together with
Um,
money.
Any other question?
Can I address the disappointment aspect? So, I don't know, maybe there are things, I know there are things you're disappointed about, but it's just not the way I think about it, right? Like, think about how we are here now and we're pointed the direction the next 20 years. First of all, obviously we're not gonna address them all, right? But we wanna have a rich set of pointers so that different people can pursue the direction that is interesting to them. And then things that we expect. We are dreaming right now. I mean, I don't put them in the frame of expectation. Subhashis didn't do verification at the level I want. Like, that's not how you think about it, right? We just look at what we feel we need in broad terms.
I mean, from 20 years back, you were dreaming something, and now you're kind of disappointed that that didn't quite either pan out or, you know.
EDA never let me down.
Okay.
Other things, but how about you?
Okay, any other question from the audience? Looking around, your last chance. If not, I have, yeah, there's one question there, if you bring the mic to him.
So thanks for the point. I actually want to ask from the system level, because it's actually mentioned, and especially I think since Joseph Sivakis published the paper about system design automation, and about if we can go from, for instance, specification level or a very high behavior level down. And I want to know, it's about, since the publication, it has been 10 years, and I want to know if, from the EDA community, if it has been addressed, or the top-down flow has been addressed, or it remains as a challenge.
Should I take that? Was it addressed to me? Okay.
Mainly, yeah.
To any of the panel members?
Okay. Because the other ones should also be involved. I mean, the thing is really with Sivakis' approach, it was you have a function and you implement the function. This has, unfortunately, two aspects. The one is we are mostly fighting with integration today. And the second one is there's always somebody who doesn't formalize. So the reality, unfortunately, and it's getting worse over time, is that the systems are not implemented as they were specified, and nobody really can tell you what the system is doing. I mean, you already see this in hardware, if you go all the way down, but you see this even more in these systems with agile and software design processes today. So Joseph was right, but unfortunately, practice didn't listen to him.
So should it...
Luca, I think you can speak, no?
Okay, maybe I'll give a shot to the answer to this question, and also combine with the very stimulating question of Subhashis. So in my view, an example of how this vertical system to implementation flow is now happening is the design of AI systems. Currently, we do have high-level specification, going down and over co-designing the hell out of all the angles of the design implementation and so on. So to me, this is really where, pushed by this energy crisis, this efficiency, extreme efficiency required, it's really happening. And it's the first time I see from the algorithmic down to the transistors, everything being optimized for an application. So this is, for me, stimulating, and it's also a big disappointment, the same, because people talk about AI systems as weapons. And this is, for me, is a huge disappointment, and it's really going in the wrong direction, but there is a silver lining. At least it's design automation to the, to the extreme.
David, you want to add something?
If I can, okay. Yeah, if I can add, maybe it was a little bit going in the direction of what Luca said. So for me, one of the main things where you can see that finally the algorithms and people that do actually hardware are really driving even the architecture and so on. So what you see, when I show you the sample of how you measure teraflops, you start seeing architectures that were not done for the general purpose. You start seeing that NVIDIA gives you numbers for fixed point, floating point 32, 8 bits. So this basically shows that they really start seeing the angle and they verify actually the different functional units for all this. And there's a clear trend also to creating this specialization with very customly optimized hardware, like Luca was talking about what you have, all these AI accelerators. So this is a very clear example for me that goes somehow in the direction of Joseph was trying to do, but like we are saying, it's so broad the field that you cannot really make the whole specification. And on top of that, the AI community keep changing their ideas. So they keep changing the topologies, the hardware. Transformers are not anymore transformers. They are mixed transformers with things around and so on. So it's very hard to follow. Now, disappointment for me is that you keep hearing, and I have heard that for 20 years, people saying, well, we have a power problem, we fix the problem, but they come up with another problem again for the power. Instead of thinking of something else, maybe they should come back to us and try to learn from the experience that if there is enough funding and collaboration, I think we should do something together. But I think this one, I keep seeing that instead of going the right direction, goes in the opposite direction. So I think we should, I have a disappointment here, and I think it's going to go on for quite a few years from what I see in the US happening. But let's see where it goes.
Okay, with those wise words, EDA has never let us down, and there are challenges ahead, so we still have plenty of job activity to do. With that, I want to conclude this panel. I know we can continue on, but we are tight in the program here. So thank you all for attending, and let's give an applause to all the panel members.